But anyhow, for those of you who do not know me, my name is Ali Kujuri, and I'm an adjunct professor at this department, Engineering Science Department, and also one of the organizers of this lecture series. I would like to thank you all for attending this 8th engineering science lecture in this academic year, and also the 110th lecture in the series since we started in 2006. My thanks also go to Agilent, formerly Agilent Keysight Technologies, formerly Agilent Technologies, for in fact sponsoring this lecture series since the start in 2006. And before I start introducing our guest speaker for today, let me mention that we'll be having, we have ordered pizza, and then it's going to be coming arrive at 5:30, and we hope that you enjoy it. Also, our next guest is Professor Audrey Bowden from the Electrical Engineering at Stanford University. In fact, I have invited her, and then after that also another lady professor will come from UC Davis, because next month will be the Women's History Month. And to recognize the Sonoma State University Women's History Month, I decided to bring also some lady professors, and also hopefully later also from the technical side. Her talk will be it's titled Optical Coherent Tomography, Lighting the Path to Better Healthcare. Our speaker today is Mr. Chuck Corley, and the title of his talk is Bleeding Edge FPGA and Digital Design, New Challenges at High Gigabit Rates. About Chuck. Mr. Chuck Corley is a multidisciplinary crossover hardware and software engineer who enjoys the challenges of making new technologies work reliably. Some of his current engineering passions include field programmable gate arrays, FPGAs, and ultra-high speed multi-gigabit digital design signal integrity. When working with customers at one of the companies, Chuck was given the nickname MacGyver.
You're supposed to take that out.
by the field engineers because he would diagnose and fix unsolvable customer system problems using grocery stores as electronic part supply depot when nothing else was available. Chuck has bachelor's and master's degrees in electrical and electronic engineering from Sacramento State University. He is proud to have worked for Hewlett-Packard, Agilent, Cisco, Mahi Networks, and Keithley Instruments. Currently, he feels very privileged to be part of the team at National Instruments, and also teaches high-speed design classes. Chuck's most recent hobby is being a project lead for Engineers Without Borders, designing and building sustainable, clean drinking water systems for native villages in the Amazon region of Peru. Here is Chuck.
Thank you. I appreciate the invitation to come and talk today. And what I'm going to talk about is just one area I work in. So if there's other areas that we want to talk about and go into, I'd be very, or the Engineers Without Borders, I'd be really happy to talk about that. You can get me going about any of those things. So the talk we're going to talk about today is how are we making computers go faster these days? And there's a lot of parts for that, but I'm going to concentrate on the CPU board. You have your CPUs, you have your internet connections and everything. So there's 3 or 4 different parts to making computers go fast. But I'm going to focus on one of the areas I work in, which is the PC boards and the connections between. You have connections between every chip on here. I brought one of the bigger ones so you can kind of see it. But every chip on there has a bus and connections to all the other chips and all the other buses on here. And each time, there's been about 5 times in my career, it seems like about every 5 years, there's another barrier to going to the next speed level. And we don't know if we're going to be able to keep going faster, but I wanted to talk about where we are now and what the newest challenges are, and give you some of the background about the history and what's slowing us down and how we're trying to break through some of these barriers. So as I mentioned, we keep having this struggle about every 5 years, and often it causes companies to go out of business because they try to use a new technology and it doesn't work, the products are delayed, and they go out of business. And this has actually happened to companies that I've worked with and companies that have competed with our company. This new struggle is happening now with some of this 5th level designs and this what's bleeding edge keeps moving up. We keep getting more and more challenging, and we figure out each time what to do, but then the bleeding edge moves up to the next level. And here's I've kind of categorized it. The 0th level is what I see when I come here and people are plugging in proto boards and they've just got bare wires going from one part of the circuit to another. It's not very high speed, and so that's the reason it works. The edge rate is pretty slow. And that's kind of how it was when I got out of college. It was just getting to the point of where we were breaking to the 1st level where you had to use 50 ohm traces, you had to have planes, you had to do everything. And that lasted about 5 or 10 years. But then when I started at other companies, we got to about 800 gigabits per second, and suddenly things like parallel buses stopped working for us. And that was about 2000. And since then, we've hit another level where a number of companies tried to go to 10 gigabits during the telecom era. And several companies I know went out of business trying to go to that level until we finally learned all the techniques and the high frequency strategies to do that. And so this is the 5th level where we're up to 56 gigabits per second. And we're finding that PC boards, it's not a very friendly place. And so where there's more challenges here. But this is a big part of making computers go faster and making the internet faster and so on. One area I work in is called field programmable gate arrays. And these are reprogrammable devices, kind of like you can write software for them, except it's computer logic. And this is another area that I work in. They're nice because they're these big, nice chips that you can put in any logic that you want, and so you can define your own computer. To talk to each other, they have these 28 or 56 gigabit links now. And at these high frequencies, there's 3 problems that are happening. Crosstalk, skew, and the PC board materials are actually causing the signals to go away as they go across the board. So, you guys like quizzes, right? Yes?
I have one quick question.
Okay, sure.
When you say PC board material,
Yes.
we're not talking FR4, we're talking more sophisticated materials, or
We are talking more sophisticated materials. We'll
like
start at
Rogers 4350 and that
Yep,
type of thing.
yep.
Okay.
And I've got a chart that will show some of those, and that's one of
Thank you.
the fixes. So, you're in an interview in a company, and they ask you what Moore's Law is. So I want to help you with your interviews. So can someone kind of give me a really brief description of what Moore's Law is?
I'll shoot.
Shoot.
Every 18 months, the size of transistor is cut in half, meaning you can fit more transistors into a given area, therefore increasing speed.
That's right, that's right. And here's a graph of that. And basically what it is that one of the founders of Intel, about 1965, kind of noticed that, hey, every year, it started out every year. He said every year we're getting twice as many transistors on the same area of die. And so either you get twice as much computing power for the same cost, or your computer can be twice as big, for or the same size for half the cost. So that's what has kind of happened with computers. They keep getting cheaper because we keep shrinking it. And this has gone on for 50 years now, believe it or not. And this ends at 2011. There's always been this fear that this nice ride would end, that our computers would stop getting smaller and stop getting cheaper. So this is transistor count. So now this is that same plot here. This green line is how many transistors you can get on a chip. But if you look at this one beneath it here, you'll notice something happening where it's flattening out. And this is the clock speed of the processors. And you know, when I got out of college, the processors, they were getting faster. You would get your 25 megahertz one year, and the next year you'd get your 50 megahertz, the next year you'd get your 100 megahertz. And so we were going up this curve. And then about 10, 15 years ago, that kind of flattened out. You're not getting anything much above 2 or 3 gigahertz now. And so there's been kind of that scare. It's like, oh, that's kind of a heat problem. Maybe we're not going to be able to do that with Moore's Law anymore either. Or maybe we're not going to be able to do that with the I/O connections between chips. And we've already run into that a couple times where we were scared that, okay, we're not going to be able to make computers go faster anymore. Now this is a completely different chart. Everybody likes Moore's Law, so everybody says that this is Moore's Law for high-speed I/O. So Moore's Law is really famous, but this kind of shows, what this is showing is the speed of the I/O interfaces. And everybody here uses USB, and you probably know that it got faster and faster over time. There's PCI Express, these blue boxes here. They were, when we first got computers and we got cards, you plug in your display card like this one, and the PCI Express, you know, Gen 1 was 2.5 gigabits, and then it's the latest, one of the newer ones is 5 gigabits. The very latest one is 8 gigabits, effectively 10 gigabits, and then 16 gigabits for the next one that's going to be coming out in the next year or two. So these cards that you plug in, they have interfaces that go to the CPU, and they're a big part of the speed of your computer. And the thought was that this year we're going to be hitting 50 gigabits. And we're pretty close to that. I went to a DesignCon this year, and a lot of the presenters were about getting to 50 gigabits, but we're starting to struggle. So there's a big concern that this curve will maybe actually going to flatten out here, kind of like the CPU curve did, because PC board materials are getting to be not as friendly. So just so you can see, this is an FPGA data sheet that I pulled up. And here you can see the max transceiver speeds. This is the interfaces between chips. And they're actually up to 30 gigabits per second. And you can have up to 120 of these. So you've got a lot of speed going different directions to all the chips around it. And that's how you talk to your display card in the computer. That's how you talk to the internet. And that's how you talk to all your peripheral devices. So here's how it used to work up to about the year 2000. Anytime you wanted to talk between two chips, you just put a parallel data bus between the two FPGAs or ASICs or chips that you want. You would latch data in one, you'd send a clock along, and the next chip would latch it. And that worked up to about 800 gigabits. And then we kind of hit a wall, and I'm going to explain why in a second. But here's what we do now for about the last 15 years, is we started to send differential signals. So you have a plus and a minus signal. You convert it to a pair, and you run it 8 or 32 times faster. So it's a lot more expensive to build this serializer. This was really simple and cheap, and we liked it, and that's why we hung on to it as long as we could. This is expensive. It has to run 8 times faster. It's a lot more expensive, but we finally found out that the PC board technology, we couldn't support speeds any faster because of a number of things, but one of them being that these different lines would run at different speeds across the PC board. And so you couldn't reliably, when the clock happened, they couldn't be reliable on when the data would arrive at the right time. So the definition of SerDes is a serializer, deserializer. So it's kind of like a shift register in, goes on, and gets put in another shift register. And here's when the last PCI was like one of the last commercial parallel buses. And at this time it had 32 data bits, and it would run at about 133 megabytes per second. But you can see with the SerDes, just one data pair running at 800 megabits would run almost the same speed as all 32 of those data bits. So if just one pair, you could get the same, almost the same speed. And then it got even better with, you know, PCI is kind of like PCI Extreme. This was like the last of the PCI parallel buses. And they actually bumped it up to 64 data bits, and they ran it, you know, instead of 33 megahertz, they ran it just as fast as they could, which is about 133 megahertz. But still, with just 4 pairs of signals running at 2.5 gigabits, you outran these 64 data bits. So that's kind of the transition. Those were the transition years when parallel buses, if you wanted to go really fast, the parallel buses kind of started to go away because they couldn't keep up. And this is a pictorial version of that same chart. You can see that PCI Express was a 30 nanosecond. Every cycle, you would get data every 30 nanoseconds. PCI X was closer to about 7 or 8. And if you're going 40 gigabits, you can't even see how long it takes. It's so much faster. It's like a factor of 1,000 difference. And that's just in the past 16, 18 years. So that kind of shows you how much faster we've gone. Now, just to compare, since you can't see these, I'm going to take away these bottom 3. And just since then, we've gone to another factor of 16 between the original 2.5 gigabit PCI Express and what we're starting to do now. So we went from 400 picosecond period to 25 picoseconds. So things have been a lot faster. We've been going a lot faster. And this is, if you brought these up on a scope, this kind of shows that. Your PCI, your first PCI cards, if this had been a PCI card, which I don't think it is, it would be going, you'd see an eye that looks this big, and you'd see 16 eyes at 40 gigabits. So now we're moving on to this 5th level of design. We've gone through all 4 of these other levels, and we can kind of figure out how to do that now. And the boards are getting reliable. But now we're trying to go up to 28, 56 gigabits, and it's a struggle, and boards are not working. And here's some of the main reasons. And I talked about crosstalk, signal skew, and signal loss. So I'm going to talk about each of these areas, these struggle areas in order. So crosstalk is about the rise time. And unfortunately, what happens is the faster the signal, the faster the rise time, and the more crosstalk you get in a shorter distance. And there's something that they call the transition electrical length. And I'm just going to go to this picture because I like pictures. So if you have a rise time that's a certain amount of time, and I'm going to say, let's say this is 170 picoseconds for this signal to go from 0 to 1. If this is, an inch long here, PC board material typically is about 160, 170 picoseconds per inch. So in the time it took this signal from go to low to high, this signal would have traveled from here to here. So that's the transmission electrical length. So in about half that distance, the crosstalk to an adjacent trace is achieved, the maximum amount of crosstalk. So if you've got another trace that's really close to this one, or maybe on top of it on a different layer, then in half this distance, you're going to have maximized the amount of crosstalk and probably completely messed up that other signal. So that's what's happening. It used to be that you could go with the old technology about 3 inches before that happened. You'd lay, and then here's an example of where people do this. When you're going into a chip, you say, oh, it's really crowded here. For a little short distance, we'll cheat, and we'll run these signals on top of each other. We used to be able to get away with that. We can't anymore. And here's all the calculations for that. Basically, in the old days, if it only went up 1 nanosecond, you could go 3 inches. But if it's going at 40 gigabits per second, you can only go 35 mils. And 35 mils is 3,500 thousandths of an inch, about that far. So you basically can't overlap signals anymore because the crosstalk gets to be a fatal level in this distance. And I should have a disclaimer that you shouldn't be even aiming for the maximum amount of crosstalk. You're already dead by that point. It's like 1/4 of this critical length. But this is a good way to kind of illustrate how the critical length has changed as you go up in speed. But this is the probably when I got out of college, this was how far you could overlap because of the crosstalk. Now this is how far you can overlap, and so you just have to. There's a number of boards in Sonoma County of people that I've helped recently that this killed their boards. So this is the new sneaky crosstalk problem where wires are close and your signals are ruined. And same thing for 20 gigabits is 74 mils. This is actually the design problem somebody in Sonoma County had that ruined their. And here's how you fix it. There's a couple different ways. You put planes in between the layers so there is no crosstalk, or you route them so that if they are on adjacent layers, you don't put them on top of each other. It's pretty simple. You just have to realize you can't do this anymore. We got away with it. Digital design, a lot of it is about what you can, you've got so many wires and they're so close together, you have to make compromises. It's what compromises you can make and which ones you can't. And this is one that we used to get away with that now at these high rates we can't. And here's my disclaimers of you shouldn't be doing crosstalk critical length is way too bad that you shouldn't get to that point. So let's before I go into this next section, let's have a quick review on how PC boards are actually made. I think this is a 20-layer board up here. So there's 20 different layers of copper running traces around this board. And so from a manufacturer, you can get, there's fiberglass. It's kind of like building a boat. It's actually like a fiberglass boat is how I think of it. You have this material that's got a fiberglass weave, you add resin to it, you heat it up, and you can glue it to sheets of copper foil. And you actually can buy it together with copper foil on both sides. You have this prepreg material in the middle that's the resin and the fiberglass. You heat them up, and then you can also add more layers by adding more layers of prepreg and more layers of copper foil. And you're basically gluing them together. And PC board materials, now here comes your question. PC board materials have a couple of important constants. One is the dissipation factor, and it's kind of like, I think of it as your miles per gallon. It's how much signal you have left over a certain distance. And then there's also something called the dielectric constant. And I think of that as the speed factor. It's how fast a signal will travel over your PC board. And a signal in vacuum or an electrical signal will travel at about the speed of light. But on top of a PC board, it doesn't go that fast. It's not in a vacuum. It's going over this material and copper. And you have the dielectric that affects how fast it goes. And so the dielectric constant is telling you this is how fast it will go. And it's what you put in the simulations. PC board materials typically range from about 2.1 to 4.9. And unfortunately, that resin and the fiberglass weave have different decay factors. And here's the different decay factors. So you're seeing the resin, it's a factor of 3.2 of the speed of light. So let's say it's about, I think that's a third basically, whereas this is a much higher factor, so that the glass weave is slower. So let's do a comparison. So this actually happened at a company that I was helping here around 2002, and it was at the end of the parallel bus, 800 megabits. This was a design. I think it was a RAM bus design, and it was running at about 800 megabits, and there was a clock trace and a data trace running on different layers, but those different layers had different decay values because when you buy these sheets, you make them a certain thickness and you vary that thickness by having different amounts of resin. And so the resin changed the decay. And it turned out with the decay at 3.6, the speed of the traces on one layer was 160 picoseconds per inch, whereas it was 169 for the other layer. So the difference over 10 inches was 87 picoseconds. That was enough to cause a circuit failure. Yes?
Do you want them to be matched up?
Yeah, you want them to arrive at the same time.
So could you change the design of the line to make it longer, put like a loop in or something, depending on
You
the
could.
speed?
you could compensate for the so when we went to fix this, there were two ways to fix it. One was to make the trace a different length.
Yeah.
Normally, we always try to make,
About the same length, yeah.
we have a mental problem of thinking, old school, that all the traces are running at the same speed, and so if you match the lengths, they'll arrive at the same time.
Yeah.
And in fact, that's a lot of engineers still think that way, and that's another thing that trips them. So if you go out now and you realize that things run at different speeds over different types of material, you're ahead of a lot of people already. So.
And would the shape of the trace depend on the clock speed, like frequency? Because higher frequencies, the more you change the shape.
Yeah, there's huge debates about angles, and I believe, and for the most part, the tests people have done, they claim that there's no difference. But what I've learned is, as you go up in frequency, things change, and I suspect it will make a difference. And I know the microwave guys that I work with all the time. I'm the one digital guy with a whole bunch of microwave guys, and I learn a lot from them. And that's how I've learned a lot of this. But you get to high frequency, that I think it does make a difference. But with digital things, you're trying to make some compromises to pack as much you can to save cost, and so we try and get away with a lot of things. Sure. Now, 87 picoseconds, this was like 1.2 nanosecond period between these two chips, so this was only like a 7% difference in the clock period, but that was enough to throw the timing off. But if you look at 10 gigabits, instead of being 800 megabits, you look at 10 gigabits, the whole period is only 100 picoseconds. And if the signals, one signal was thrown off by 87 picoseconds, you're nearly into the next cycle. And at 40 gigabits, you're 3 cycles. Your data signal arrives 3 cycles late. And so this kind of illustrates why parallel buses kind of died. Because parallel buses, typically, you do have to run them on different layers. And the running of a differential pair on the same layer, that's what fixed this. That's how we got to level 2 and level 3. That's how we broke away from level 2. Okay, so I've got a little video here, and this is kind of a quiz also. So we hired some expert snowboarders to illustrate this PC board effect. And I want to see if anybody here can recognize what PC board effect is like this snowboarding video. So we have 2 snowboarders, and they're each going down in parallel down a snow slope. And one of them is going to be going out into the sun, where the snow is softer. And the other one with the camera is where the snow is colder, where it's in the shade. And this is like I'm illustrating this as a PC board effect. So I'm kind of going to ask you if you can think of what PC board effect this might be like, that you might have heard of. It's different decay. Marissa wins. She was in the shade. So, okay. Now this is on the same layer. They're both on the same surface. Yet one signal. This is Eric Bogatin is be the signal. So you guys be the signal. Tell me why this signal is slower than the one with the camera on the surface with the same decay. Has anybody heard of a PC board effect that's like that? Okay. So, just as a disclaimer, as you can guess, those weren't professional snowboarders. That was me and my daughter. Okay, so the effect. So I told you about the effect with the different decays, where you're on different layers and the speed is different. Now we're on the same layer. What's going on? Why is one signal faster than the other? Well, there's pockets. Now we're going so fast that it actually, on this next speed levels, that when you hit the resin, the signal actually go faster. And there's pockets of resin. And then when you hit the fiberglass, you slow down. So the signal is speeding up and slowing down, and it's going over these holes where there's only resin. So with certain fiberglass weaves, you get these pockets of resin. And you see this guy is going over the slow snow, and he slows down because the weave is slower a decay that is slower, whereas this one speeds up and then speeds up and then speeds up and then speeds up. And this is called weave effect. And this was, this started to trip people up at that fourth level I mentioned. This is where sometimes people would get their PC boards back and their first prototypes, they would work great. Then they would go and order another run, and these traces would be aligned slightly differently on that next run, and those boards wouldn't work. And so you had these unreliable production runs of boards. Some boards would work, and some boards from the same panel would work or not work, because the weave would be different on each panel. And here's kind of a, they're showing here the glass weave and the resin have different values again, and you can see there's pockets of weave, and here's the traces going over the different places where there's resin or there's not resin. And here's a picture of showing, so then this is how we kind of got through the fourth level, is that we started using weaves that didn't have pockets. And there's what's called mechanically smashed. So that, and this is about the size of a trace. This wire is about the size of an actual trace. So this is the kind of weave, this is like one of the worst weaves here, and that's one of the better weaves. And that's how we got through the fourth level. So here's some pictures of that. And this is only a 10% imbalance. So one strip has 10% more resin, the other strip has 10% less. And this is like a scope plot where you can see this signal arrives sooner. These signals started out at the source going from low to high at the same time. But by the time they arrived at the receiver, they were different in time. And the picture over here is really nice because you can see at low frequency, that didn't used to be true. When you were below about a gigahertz, they actually would line up. But then as you got higher and higher in frequency, this difference, this effect starts to kick in. So that's why when we transitioned from trying to break that 800 megabit barrier and we started to have effects like this, it kind of killed the parallel buses. So now if you had a scope and you have an eye diagram, and this is, you're going 1 and 0, so if you have a nice big eye here, that means you've got good data, you've got a good noise margin here. But that same plot that you saw before, this is what it causes the eye to do. It closes it down, and it makes your data unreliable, with only this case of 10% imbalance. So that's what's happening with weave effect. And this is another way of showing it. These are actually what's called Timedomain Reflectometer traces. So we're sending a pulse down there, and it's how we usually check PC boards to see if the impedance is what we expect. But we're seeing here, because there's more resin spots and less resin, that this board actually, this is when it's going over the holes of resin and without resin. Whereas this is the other weave we saw. It's nice and flat, it's not as bumpy. And not only is the impedance changing, but the speed of the trace of the signals over the trace is changing for every time there's a bump here. So that's another way of kind of looking at the trace, and you can actually see those pockets. So this has been a big area of discussion the last 5 years. It's like, what can we do about this? Well, we've kind of discovered through experimentation that there's a couple of weaves that are nice and tight that this problem isn't as bad. And this has helped us to make, in this fourth level of digital design, signal integrity design, that's how we've kind of gotten through that speed level. And these are mechanically flattened. So this is how, if you normally do it, they tend to bundle up. But if you take a machine and you sit and smash them, then you get a lot less holes, they're a lot flatter. And this is a lot of the materials, they have a dash MS, which is mechanically flattened materials. This is good for another reason. When you have the very small vias that are blind and buried, they need the fiberglass to hold on to. And so that's another reason that mechanically flattened materials have become a new material that's available to us to help us through this speed. What's another way you can do it? Oh, well, if you kind of twist the traces a little bit, they average out going over the pockets. Both traces will, as they travel, go over the same number of pockets. And so they'll kind of be the same speed. So if you take a panel, and this is a good board because this board is actually a whole PC board panel. So if you had smaller boards, you would make a whole bunch of them on this panel, but this is about the size of a typical PC board panel. So when you're making a bunch of PC boards, you can twist them, and then you cut them out at the end. That works when you have a small board, but when you have bigger boards, you lose a lot of the PC board material, and it makes these boards cost about 50% more when something like that happens. It's one of the ways people have done it. This is the way that Intel is now having people doing PC motherboards do it. It looks like the PC designer was kind of drunk because it's going, you know, tracers are kind of going sideways like he's not driving straight. But this actually accomplishes the same thing. It makes the traces go over kind of an equal amount of surface with a number of pockets, and so they arrive at the destination at the same time. PC designers are not a big fan of this. It makes their job a lot harder. There's something at the receivers called equalization. This may be a help in the future. The receiver could, you know, add a delay in there, automatically detect it. And I think that's going to be one of the technologies that's probably going to come in the next generation of FPGAs and these SerDes, is that they're going to have to work on this, because with each board being different, we're not sure we can make them the same anymore. They might have to do this.
Now, if you add a delay, does that decrease processor speed?
No, delay is, you just, you know, it's like a conveyor belt. You just shift it a little bit. It's still running at the same speed. You got two conveyor belts next to each other. You just shift, you know, okay, this conveyor belt's out of phase with this conveyor belt. You just shift it, and then they're in phase. And then the other way is use materials that minimize skew effects. We're going to talk about this a little bit more. So I mentioned that people had gone out and built boards to try and figure out how to get through this next level. And these boards have lots and lots of identical parallel and vertical lines, and these are all really expensive connectors down here. So we're putting signals in one board and coming out the other board, and then measuring what the difference is between the different materials. And here, someone actually took 17 different materials, built 17 boards like that picture you just saw, and they measured how much skew, what the worst case and best case skew was on each line that was 14 inches horizontal or 9 inches vertical. So a company, to help engineers build these boards, because this weave effect was so bad, they said, you know, which boards are, what kind of materials are the best? And so, you know, this is the one you don't want to use, because you know, 123 picoseconds, even at slower rates, is terrible. These are some new materials that are being made. What they're doing, I believe, is they're making the weave and the resin about the same decay values, so it doesn't matter which one you're over, the speed is the same. Yes?
As you go from the top to the bottom, how does the cost factor change?
Pretty much as you probably would have guessed. This is the cheapest material, though not totally. You know, this is inexpensive. This is inexpensive. This is actually more expensive. So it's not. This one, I know this one was specifically made for skew, that it's not necessarily more expensive. So I'd have to, you made me think there. Yeah, actually, some of them are backwards, because Megtron 6 is a faster material than Megtron 4. So that was I think that was one of the reasons they did this study, is that material wasn't necessarily, it didn't match price.
Okay.
Yeah, no, that's a good point. Okay, so that was the weave effect. Now I'm going to go into the third thing that's the big challenge, is someone stole my signal. So at higher frequencies, the signals lose voltage. In the good old days, you could have a 3.3 buffer on one side of the board, drive 3.3 volts out, and on the other side you would expect 3.3 volts to arrive. But at very high frequencies now, that's not true. If you're going at 40 gigabits, you might not get much signal at all. This started to happen above 1 gigahertz. The properties of the resonant glass weave, they become much lossier. And let's take a look at that. So there's two main contributors here, and they're added up. There's the dielectric loss and the skin loss, and this is both of them together. And when you look at this chart and you realize that this scale is in decibels over here, if you're familiar with decibels and you see that after, say, about 24 inches, you've lost 45 dB of your signal, To translate that to volts, if you started out with 1 volt, you would have 0.5 of a volt left. And 0.5 of a volt, with the technologies that we have, is not enough. It's gone. I think the very best technologies I've seen are some of like the Xilinx ones. I think they claim they can do about 36, 37, 38 dB of loss and still be able to reliably do the signal. So that's terrible. Your signal's gone by the time it gets across the board. And that's what we're having to deal with. The other thing to notice here is that's only 12 gigahertz. We're talking about 56 gigabit, which is like 26.5 gigahertz. So this just keeps getting worse. And what you're going to see is that as these speeds increase, you just can't transmit the traces very long. So everything's going to have to get shorter, or else you're going to have to rebuffer it time and time again. So everything's going to have to get smaller. And here's some different materials. You mentioned the microwave guys. They like this 4350.
Yeah,
I think that's the one you mentioned.
right.
So this is the loss per inch. So you can see, and this is even high performance FR4. So this is low loss FR4. It has about 1 dB per inch. So in the first inch you've lost, if it was 1 volt to start with, you've lost 1/10 of a volt. It's like you've lost more than 10% of your signal just in an inch. And this is actually a 20 mil wide trace. This is an RF trace. Digital traces are more like 4 mils, so it's even worse for your typical digital trace. So here's that big, cheap kind of material we call FR4, and then over here is all the new materials. And this scale is going to be about loss down here. But I just wanted to give you the overview of where FR4 was in relation to the rest of this. So here's all the new materials people have come out with to try and fix this problem. And these do kind of go in order of price going down this way. So these tend to be the more expensive ones down here. So the lowest loss is down here. The higher loss is down here, though compared to FR4, which is way out this way somewhere, these are really low loss. But this just gives you an idea. These are the 20 or 30 low loss materials that companies have come out with to help us with the signal loss problem. So the other side, so that was dielectric. There's 2 parts of the signal loss. It's you lose signal in the dielectric of the material. Then also the copper. If the copper is rough, that's another factor. So if the copper is rough, you lose more signal. If the copper is smoother, you lose less signal. So if you go back to that plot, you can see the skin loss is a secondary effect compared to dielectric. But if you make this dielectric loss less, suddenly the skin effect is very important also. And here you can actually see we're actually making the copper smoother. And why was it rough in the first place? Well, because that makes it glue better. When it's rough, they purposely actually roughed it up. In the old days, it didn't matter because it was low speed before. And so we would rough it up, and that helped it hold on, and you don't delaminate, that doesn't come apart. Now we've had to come up with new types of materials where you can have a much smoother, like 1.2 microns in this case versus 3.5, so that the signal, you don't have as much loss going across this higher loss material, copper. And here's the ways you can specify it, and you can see the different amount of roughness. They call what they call very low profile, super low profile. But that's another factor of making sure you have some signal left by the time it gets to your receiver. So what can we do, since we seem to be hitting this wall where we're not sure we can make traces on the PC board go any faster? What can you do to still speed things up? Well, there's something called, this is what we use now. It's called non-return to zero. It's a technique of where you're going 1 and 0 every cycle. You're either going to 1 or you're going to 0. And so every clock period you get 1 bit. But what if you could do it where you have 4 different levels? So every clock period you get 2 bits. You've just sped it up by a factor of 2. And here's how it works. You have 4 different levels, and each level is 2 bits. So you get 2 bits every clock period. So you haven't sped up your signal, it's going the same speed, so you don't have more loss, but you've doubled the data rate. And here's how it works. So in one period here, you get 2 bits of data, whereas in the old NRZ PAM2, you only got 1 bit of data for every period. So that's the techniques. It's kind of like, you know, that in the computers, I showed you the clock rate. It stopped going up, so we started adding more cores to the computer. You got 2 cores, 3 cores, 4 cores, 8 cores now. This is kind of the same. Now we're using modulation techniques so that you'll get more speed, but you're not going to get it at a higher rate. So some of my conclusions are, we're still increasing speed, but it's getting harder. The crosstalk hazards are kind of sneaky. They get on you and you don't know that they're going to be there. You push up in speed, and what worked before doesn't work. The interpair skew, where you have 2 lines and they're going different speeds even though they're on the same surface. We're using new materials, and the highest rates are definitely going to require a combination of techniques. All the things you said, probably weaving and new materials that have the same decay for both materials. And then at higher frequency, we have a number of problems. The dielectric in the material has a lot of loss. The new materials have less loss. There's skin effect, we're smoothing the copper. And then we're starting to use, just like we did with wireless technologies that used 256 QAM, we use PAM4 now to give more bits. Any questions? Yes?
To get more speed, so you're thought of into optics?
Yes. In fact, you see this board up here has gone to optics. Yeah. You still have to get the bits there somehow. You know, usually from even these chips, a lot of these chips now, they have little PC boards inside them because the die is tiny, and then you have to break it out, and then you have to get it. These are optical transceivers down here.
Pretty big.
Yeah. Well, they're getting smaller. This is 10 years ago
Okay.
technology, but still, and they're pretty expensive. There's been this fight between optical and electrical,
Yeah.
and we keep pushing electrical. It's like the phone wires that run to your house. It would be better if they were optical.
For speed.
Yeah, for speed, but electrical's cheaper, so we keep trying to push the electrical higher. And so we actually had optical in some of the products we had, and we took it out because it was so much more expensive, and we're putting in electrical because we're using some of these techniques to make the electrical better at a lower cost. Yes?
Would denser integration help here? Because if you bring some of these pieces together, the transistors on together in one dial on, it could be probably help this thing, right?
Yes. Distance is becoming important. I mean, you've seen some of the Cray supercomputers that were circular because they were trying to get the things so close. Now that same thing is happening on the PC board.
Right.
And sometimes we may have to have where we glue several dies together instead of having it go to the board that we're having wire bonds or something between them. In fact, the newest Xilinx chips, they actually have several dies in the same package that are glued together. So yeah, the distance is becoming more important, and they're coming out with the new cards that are, I think we're just coming out now. Most cards are PCI Express Gen 2. We're coming out with Gen 3 now, so some other boards are coming out, and they're working on Gen 4. Gen 4, they believe the distances are going to have to be smaller. The PC board material, they're going to have to go to some of those higher cost materials just to get the, where they plug in the card to the chip. Everything's getting harder. The distances are getting harder to go at those speeds. And so we're looks like we're hit up against a wall, but we'll just find more tricks to make it work. Yeah. Yes?
Is there a speed limit with electrical signals?
The speed of light. And then, as I mentioned, depends with the decay. Some people actually specify that to make the signals faster. I mentioned the Cray computers of old days. They realized they were like the first ones to start to realize that and start pushing things closer and starting to use different materials. But A lot of it is all relative, though. If you're pumping signals down there and they're all in the pipeline, in some ways, when they arrive, it's okay. It's just a delay in the conveyor belt. So as long as you can still do several things during that time. So, yeah. Sir?
I know you're using differential lines to transport signals around. The microwave people especially run into grounding problems. In the digital boards, what kind of grounding problems can you run into?
All kinds of problems. The one nice thing about differential signals, or there are many nice things about differential signals. One of them is that as long as you put it along a similar path, anything that happens to one happens to the other, and you're measuring the difference in the two. And so the ground plane doesn't have as much of a difference, but the signals themselves, you know, it's a differential measurement between the two voltages. So that kind of helps you there. But because the voltages are so, part of the voltages are also very small.
Mm-hmm.
And so now if you have grounding problems and you get voltages, any crosstalk into them, crosstalk becomes more important because of that also. Because now it may only be 400 millivolts voltage swing because you don't have time for it to go 3.3 volts. That takes many, many times more. So, but overall, as long as you're on one board or on one chassis, you tend to have the same ground and you don't have grounding problems. When you go out the front panel, then the reference, the thing you're talking to could have a different ground level. And you want it to have, if it's differential, it could be shifted somewhat,
Mm-hmm.
and it's still okay. You have a range. But if it gets out of that range, then it's bad. And that's often, I mean, that's why most of our telecom is optical now. That's one of the reasons.
Thank you.
Okay.
So at the 56 rate, what you are talking about, it seems that we need now to stick with with only, shall we say, serial type of buses and so on, right? Rather than the parallel?
Oh, parallel buses, for the most part, went away 10 or 15 years ago, with the only exception being, somewhat being the RAM. There are some, they're still trying to tweak that up, but I think the next generation of RAM actually might be differential also.
Okay.
So yeah, for most high-speed signaling, that's why you saw, 160 ports, high-speed ports on that FPGA data sheet, is most of the communication between chips has all been serial now,
Okay.
for starting about 15 years ago, 16 years ago.
Okay, good. Thank you.
Sure. Yes?
I was wondering, like at the backplane level, how is the signal integrity, how much of that signal integrity issues are contributed to the backplane? Because you have a lot more lines and traces on the backplane. So is it something that drastically the whole convention of doing the layouts on the backplane is different?
It all really is the same. It's just the degree, it gets harder and harder. I know that in Telecom Valley, a lot of the backplanes had crosstalk problems back when the speed was below 800 megabits per second. And then as the speed went up, it gets worse. A lot of times the backplanes, because you're going from one card to another, they have a lot of horizontal routing, and you have no choice but to separate those with ground planes in between. So you don't try to do this trick where you have two routing layers on top of each other where you could put signals on top of each other. So basically, most of the time in backplanes, you can't save layers by having two layers be adjacent to each other where they can crosstalk into each other. So backplanes, you don't tend to get too big of a problem because you already had to deal with the crosstalk problem. You can kind of cheat when all your signals are going in different directions. Ones are going this way. They don't cross-talk into each other that way when they're at 90-degree angles. It's only when they're going the same direction that tend to get crosstalk.
Right. At this time, I would like to thank Chuck for his very broad experience that he shared with us. Really, I learned a lot out of it. Let me say that. Yeah. So, and I hope that it was also instructive for you guys. So let's give him a hand then.